Hello again, this is Moe Shahram, and we are going to continue covering chapter one. So far, we talked about the essential scientists in the history, and now we are going to talk about scientific activity. Before we do that, we can ask ourselves, what is science? Well, we can say it's the way we think about our environment, our surroundings, to understand the physical environments around us, and whether we can see it or we can sense it or we can not see it, but it's there, which actually impacts our lives and our emotional and physical behavior. And the question is why? Why do we need to do that? Well, two major reasons. One is to survive. We need to survive because we need to know what nature does, what phenomena in nature is harmful to us, to protect ourselves against it. There are many phenomena that are harmful to our existence, from earthquake to volcanoes to radiation, many phenomena out there that we have to protect ourselves against it. So once we do that, then think about what is really out there and how the nature works. So we have to satisfy the curiosity. That's another reason. So these are the two major reasons that we really do science and scientific activities. And how do we achieve and understand our environment? Well, we have senses. How do we use our senses to understand our environment? We have sight, taste, touch, hearing, smell, and intuition. These are the things that we use to understand our environment and the physical phenomena that happens around us. But can we see everything? Can we hear everything? Of course not. There are a lot of things that happens that are outside of our natural physical senses. We have to come out with instrumentation and technology to help us to sense and understand things at a very small scale as well as very large scale outside of the realm of our senses. Once we do that, we need to find out, is there any pattern or repetitive phenomena that we can understand from that physical phenomena. Physical science contains many disciplines. Itself is a subset of natural science. Now, natural science consists of, physics, chemistry, biology, geology, behavioral science, all these other disciplines of science. But the physical science is a subset of that, which basically deals with physics, chemistry, geology, and astronomy. So this is what we are going to actually talk about in this course. We're going to cover these disciplines and try to understand the fundamentals behind them and see how it impacts our everyday life. The process of doing that, we are going to see what are the overlaps between these disciplines. So this is where the integration of these science come through, because a lot of phenomena that we experience every day may be a combination of one or two or more of these activities. And we need to understand them and find how they relate to each other and what are the overlap. We try to bring examples and applications that clarifies and illuminates these overlaps. So if we really look carefully around us, many phenomena that we see are repetitive and they're cyclic. They have a cycle. They go through the cycle. And some phenomena go through the cycle of a very short period, and some goes through the very long period. Some of them we don't even recognize because the period is so long that it just beyond our recognition. So one of the important things is to recognize these patterns and find the cycles and try to measure them and quantify them. Because if we can measure and quantify phenomena, then we can thoroughly understand it. Otherwise, we really don't have that much knowledge about that particular phenomena. But how do we make measurements? Well, we observe, okay? First, we observe because we use our natural senses. Now, observation can be very casual, or it could be very thorough. Scientists, when they make observation, they make a thorough observation, just like Sherlock Holmes. When there is a crime, and if you and I go to that scene of crime, we may just look at the surface of what happens, and that basically would be the limit of our observation. But for example, when Sherlock Holmes goes to a scene of crime, he sees things beyond what is apparent. And that is what scientists do. We need to look beyond what is apparent. Okay? So we make measurements and then we quantify that. But how do we make measurements, and what references do we? When we, for example, want to measure the length of this table, well, we take a tape measure or a stick. So we have some reference. And that reference is important because if we don't have that reference, what I measure with an arbitrary means and what you measure is going to be totally different, and we never agreed. The important thing is that we have to have references. We have to have standards. So we have standards for measurements, and those standards are called fundamental standards. And we assign a unit to these standards. 4 fundamental standards are length, mass, time, and charge, electrical charge. For example, for length, we just assign a symbol L, sometimes D, sometimes X, but we have to have a symbol to represent that length. And then for the unit, we use meter. Now, what is meter? Well, scientists gathered and said, hey, we all have to reference against one thing. In the past, it was length of an arm or length of a foot. But now, with the advent of the modern science, they had to come out with much more sophisticated and detailed standards and references. For example, we know that the light travels at a constant speed, a very fixed speed, and we can use that to say, oh, okay, the distance that the light travels in very, very, very tiny fraction of the second, that we call it meter. And that fraction of second is 1 over, okay, this number right here. We use that, we put it in a, archive or a bureau of standard. For the mass, M or kilogram, and the mass of a cylinder of iridium, specific size of iridium. We use that as a standard. Time, second. Time is something that repeats, right? So what do we need to use as a reference? We use something that repeats. Cesium atom oscillates. The oscillation of cesium atom, we can measure that and then use that as reference for the second. Then we have electrical charge. And then what do we call that? We call that Coulomb with the capital C. And then we use a charge of 1 electron as a standard. So these are the standards that are established back in 1791. And they call it System of International Unit, SI. So when I say SI unit, that means System of International Unit. And then this was extended to cover for temperature. That's the fundamental standard. So temperature, we use a thermometer, which tells you what is the difference between a temperature at freezing point of the water and the boiling point of the water. That's what we use, Kelvin. Of course, there are other thermometers like Celsius, Fahrenheit, which we will talk about later. And then when you dealing with atomic scale elements, you have to be able to find out what is the amount of substance you're dealing with in chemistry or in physics. So we said, okay, let's take one reference. This is carbon-12. Carbon-12 is abundant in nature. So we use that and we say, oh, let's measure, let's see if we have 12 grams of this, how many of atom in there. So we measure that, we see it's 6.02 10 to the 23 atoms. Okay, that's Avogadro's number. So that we use as a reference and say, okay, a mole of, for example, helium atom, it's the mass of the element, that helium atom that contains this number of helium atom. And then for intensity of the light, how intense it is, how bright it is. So we can use the luminosity, and we use candle for that. And that's where we measure how light is emitted from a source in three-dimensional space. So those are some additional fundamentals. So these are all fundamental units. And then when we do measurement, we have to always identify them by their unit. So if we are measuring a distance from A to B, we have to say that is about 4. Now you have to say for what? 4 inches, or if you're measuring in centimeter, so that would be roughly 4 times 2.5. So that would be about 10 centimeter. So we need to make sure that the units follows the number that we measure. When we processing a measurement, for example, against another measurement, let's say we say I'm walking 5 kilometers in 1 hour. What does that represent? That represents a distance covered in time. Okay, so I can convert that to the SI standard. So in SI, you have meter per second. So that represents a velocity or a speed. So we need to treat the units just as we manipulate the numbers. We have to manipulate the units as well. So when you say your speed is 1.4 meter per second, what happens in an hour? Okay, if you go with that speed, then you have to multiply that by 1 hour, which is 3,600 seconds. So look at these numbers that are multiplying. Well, this has meter per second, this has second, and this second cancels out. So you're left with meter. So it is very important to treat the units in their arithmetic manipulation, just as you do the number. You may have units that are more complicated than fundamental. It is a combination of them. So if you're talking about force, you're actually talking about combined unit of the fundamentals that gives us a unit of other quantities, other parameters, things like energy, power, and so on. As I mentioned, in the old time, people used certain references, like the size of your thumb as an inch, or the size of your foot as a foot. And that was the British unit. We still use some of this in the United States, but most of the other countries using the standard unit. Those are actually based on 12. A foot is 12 inches. A yard is 3 foot. You can see in this table how the British units are used and what are their relationship. So unfortunately, we have to deal with that. Sometimes we have to use British unit, and but we always try to convert that to SI unit, which is the scientific preferred unit. Because the scientific unit, SI unit, it's advantageous because, first of all, it's simpler to deal with. And because it's base 10, we have to know how to convert. And we will do that in the process. Of course, there are conversion tables, conversion programs in your cell phones. So the important thing is always in this course and later on in your life, please, when you talk about a number, put the units behind it. Because if you don't know what's going on. I say I'm 70. What do you think? The first thing comes to your mind is I'm 70 years old. Well, that's not what I meant. I meant to tell you I am 5 feet and 10 inches tall. That means 5 feet is 60 inches plus 10 inches, that is 70 inches. But I didn't give you the inches, so you didn't know what it is. Okay? So make sure you always treat the number with the unit. So here's some conversion factor of units. For example, the length, mass, volume, and time. From British, you go to SI unit. Now, if you express meter in centimeter, that is basically a subset of SI units. So you need to express that in meter. 1 inch is 2.54 centimeter. 1 pound is 454 gram. And 1,000 gram is 1 kilogram. So you need to be able to make those conversions. So here's some examples here. How many centimeter in 5 feet and 10 inches? We just had that 5 and 10 inches. That's 70 inches. So we know 1 inch is 2.54 centimeters. So we get 70 inches times 2.54 centimeter per inch. As you can see, inches and inches cancel out, and that comes out with 70 times 2.54. That is 177.8. You can do these other ones, okay? So I'll let you guys try those and make sure you do, because you're going to see this kind of thing in the quiz. And the table of conversion is here. You can just use the programs that are out there, but I encourage you to use these for a few of them so you get a feel for how to make the conversion. In treating the numbers, when we measure, we may come out with a number that has many digits. How do we write this? Well, we try to use power of 10. And that power of 10 is very powerful and important to easily express the results. It makes life a lot easier. As you can see, when we talk about the significant figure, it becomes very useful. Here we go. These are the names for these power of 10. You probably heard about mega was a million, right? 10 to the 6. Kilo is 10 to the 3. Okay. Giga is 10 to the 9, and so on, as you can see. And then if you go down and the smaller and smaller units, you have milli, 10 to the -3, or micro, or nano, or pico, 10 to the -12. Now we're getting to the size of the atom, and 10 to the -15 femto, we're getting to the size of the nucleus of atom. So it's very important, and I have a nice video here that I'd like you to watch, and let's play that. Let's go ahead and watch this.
The picnic near the lakeside in Chicago was the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide, the distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is a kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the fourth meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake, 10 to the fifth meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the sixth, a one with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. Arrival to see the whole Earth now, just over a minute on the journey. The Earth diminishes into the distance, but those background stars are so much farther away, they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the sun, followed by the massive outer planets, swinging wide in their big orbits. That outer orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one of the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan, 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely sea, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next bowl, a proton in the nucleus of a carbon atom beneath the skin on the hand of a sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we were entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. A capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon the vast inner space. At last, the carbon nucleus, so massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks in intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
Okay, 40 powers of 10 covered everything from the subatomic domain all the way to huge galaxies and super galaxies and so on in space. In this course, we're going to touch upon some of the phenomena that happens in these domains. It would be a very brief survey. So now let's go back and talk about measurements. So what do we do when we make a measurement and how can we benefit from it? Well, let's start with a simple case, Q, 10 centimeter by 10 centimeter by 10 centimeter. So each side has 10 centimeter. So from there, we know that we can measure the area of each side, which is square, 10 by 10, which is 100 centimeters. Or we can find out what is the total area of the cube surface. So because we know we have 6 sides, so we multiply by 6, you have 600 centimeters square. And then we can also find out what the volume of this is, which is 1000 centimeter cube now, because centimeter multiplies 3 times, right? So what can we learn from these? We know from our chemistry that, 1 liter of water is equal to 1000 centimeter cube, which is the size of this cube right here. This can contain 1 liter of water. And that 1 liter of water, if we can weigh it, it's going to be 1 kilogram. And then obviously the fraction of that would be 1 centimeter cube, which is 1 milliliter of water, and that's equal to 1 gram of water. So these are all the information that we can gather from this measurements and more, actually. What else? Well, let's just look at the cube size 10 centimeter, and then let's extend that to 20 centimeter, and then extend that to 100 centimeter. What happens to the area? What happens to the volume? Well, the volume and area, we know, is area is 600 for 10 centimeter. it goes to 2,400 centimeter square for 20 centimeter side. And for 100 centimeter side, it goes to 60,000. And then calculating the volume, you get 1,000 centimeter cube, 8,000 centimeter cube, and 1 million centimeter cube. Now, let's just divide the area by volume and see if that gives us some information. When you divide area by volume, for 10 centimeter is 0.6. For 20 centimeter, it's 0.3, it's less. For 100 centimeter, it's 0.06, even less. So as you increase the size of that cube, the ratio of the area to volume decreases. Interesting, right? So from there, we can actually deduce that, for example, if you have 1 kilogram of raisins and 1 kilogram of potato, which one would have more surface area? 1 kilogram of raisins. These are some of the things that can reveal from just the simple measurements of a simple cube. We can ask questions about which one of these metals are heavier. What would you say? Think about it. Think about the question. Which one is heavier? Can you tell the answer? No, because this question is not valid. It's a wrong question. I didn't tell you how much, what volume of these. So I need to give you more information for you to answer this question. So the better question is to ask, how dense is this element? And the density has to do with the mass of the object divided by the volume of the mass. We know is a kilogram, and volume we know it's meter cube. So that would be the unit for density. And this is called rho, which is the symbol for density. So now you can ask which one of these is denser. That's a valid question. So iron has 7.86 gram per centimeter cube. Gold is 19.3. Aluminum is 2.7. So as you can compare, you see the gold is dense. For example, when you talk about density, you can always write a sentence. Say, okay, density is a ratio of the mass of an object to its volume. Well, every time you want to write that down is a big sentence, right? So what do? You just use rho is equal to m over v, because you assign a symbol for mass, you assign a symbol for volume, you assign a symbol for density. So that's how you do it. Okay. Now, once you do this, then you're dealing with a relationship, a formula. Now, the formula and relationship can be written in many different ways, depending on how many variables are in there. Okay, so just like if you have A is equal to B times C, you can say, well, if I want to find B, I say B is equal to A divided by C, right? And if I want to find C, I can say C is equal to A divided by B. So all these three ways are valid formula, and you can express that. And you're going to see things like this in some of the quizzes. So follow the same logic. All right. So for forming a scientific activity and scientific method, you need to basically start with some assumption, some idea, some educated guess. If I, for example, hit this ball with the baseball bat, it's going to go through this trajectory and it's going to land a certain distance from here. So that would be your kind of educated guess. And then we call that a hypothesis. Then you say, okay, let me do it and see if my hypothesis was right. So you start hitting that ball. You projected that it's going to land 100 yards away, but it landed 50 yards away. So your hypothesis was wrong, but that's okay. Hypothesis can be wrong, can be proven to be wrong. If you cannot prove it to be wrong, that's not a hypothesis. It's okay that the hypothesis is wrong. But what you do, you make the measurements and you say, wait a minute, I was wrong. So what I'm going to do, I'm going to go back and revise my hypothesis and do it again. And this time you get closer. Okay, if you're wrong, then you go back and revise it until you basically prove that your hypothesis is okay. The process is that you form a hypothesis, you do an experiment, and once you show through many experiments that is okay, then you have made yourself a theory. And that theory can be shared with others. And they say your colleague, your classmate, okay, you go try it and tell me what you get. And he goes, try that. And you call your cousin somewhere else. So can you try this and tell me what you get? And if that thing happens for everyone, then you can actually start building a law or a principle. Okay, so you need all of these to develop a scientific method. So let's define some of these terms here. Hypothesis. Hypothesis basically is an educated guess. And it can change, is a tentative. Or you should be able to have a test to prove it wrong. So when you hit the baseball, you know that you can measure it. And if it's not as you expected, so you were able to prove it wrong. But if you couldn't do that, that's not a hypothesis. So experiment is observation and collection of data. Once you prove the hypothesis and it basically confirmed by many, many people, you can call that a theory. However, that theory can change over time. Many theories have been challenged and changed. Remember the geocentric model theory, every planet orbiting around the Earth? That was a theory for many, many centuries until the theory of heliocentric by Copernicus challenged that. Said, no, wait a minute. Based on these observations, sun in the center of the solar system. So theory of a Big Bang from previous century, starting the theory of a Big Bang, now a lot of challenges proposed. And theory of evolution of natural selection is theory. Someday, maybe 50 years, 100 years, somebody comes along based on the new findings, they challenge that. Now, when you talk about the law, this is something that observed throughout the history, has not been challenged, and has been repeating time and time. Therefore, we can call it a law. Newton's first laws, Newton's second laws, third law, Newton's universal gravitational laws of thermodynamics. Those have not been challenged. Principles, now it's same as law, but for a specific application. Now, a specific application, for example, Archimedes' principle applies to the buoyancy. When an object is inside the fluid, there's a force of buoyancy pushing it up, make it less heavier inside the fluid. Looking at this scientific method cycle, we start with observation. So whatever knowledge we have, we use that. And whatever data is available, we use that. And then we form a hypothesis, educated guess. And then we go do experiment and we get some results and we test it against our hypothesis. If it is fine, then we move to the next stage. If it's not, then you go through the cycle again until you converge and your hypothesis approved by your experiment. Then at that point, you build a theory. And that theory further is going to be experimented by many, many people throughout the history. And if it needs to be, has to be revised. Theories can be revised as well. Once that theory is revised, then you can go to next stage. You can say, okay, this theory is proven by so many experiments, and then it becomes like a scientific law. That's how the scientific method cycle works. Now, when we collect information, when we rely on our biological senses, we could be in trouble because our senses can deceive us. For example, certain things we won't be able to see well or hear well. Okay, so we really cannot totally rely on our biological senses, and we have to come out with instrument that verifies our measurements by our senses, or if it is outside of the scope of our senses, it still can make the measurement and give us a result. So one example is our optical senses that can deceive us. Very simply, looking at these pictures, you can interpret it a different way, and both ways could be okay. What do you see here, a rabbit or a bird? For example, in this picture here, how many black dots can you count? Can you just look at the picture, see if you can count the number of black dots? It's an optical illusion. And what about this one? Look at the center and move your head forward and backward. What do you see? Things seems to be moving, where in fact they're not. What about these lines? Are they parallel? What about these zebras? Two zebras have one head. That's how we have to rely on instrumentation to help us to make proper measurements. Once we do the measurement, we get numbers. Now, how do we handle the numbers? So let's say we kind of multiply two numbers, and we use calculators all the time. Two numbers here, I'll pair 2.756 times 1.20. And you come up with this number here. I get 3.3072. So the question is, how many of digits should I keep? What is the significant figures? Well, if you look at these numbers, the first one has 1, 2, 3, 4 significant figures. The second one has 1, 2, and because there's a 0 here, we can have to count that as 3 significant figures. So when you multiply these two, that means this one on the left has 4 significant digits accuracy. This one has 3. The products cannot be more accurate than the least significant figure in this multiplication. So you have to only consider 3 significant figure for this one. So you get 1, 2, 3, and that should be enough for the answer here. So that would be 3.3. Now, as for this digit, you look at the digit after that. So we are looking at this one. If this is less than 5, you just put the number as is. But if it is greater than 5, so you need to add 1 digit to this. Instead of 0, in this case, because 7 is greater, so you have to say, so now you have 1, 2, 3 significant digit for the answer of this number. Take a look at this example and other examples here. A number like this, how many significant figure do we have? Well, we need to make sure how big that number is, which is represented by these decimal points, and how accurate that number is, which is represented by the number of significant figures. Here we have, because you have a decimal point here, you ignore the leading zeros. That doesn't count as significant figure. You have 1, 2, 3, 4, 5. And because you have these zeros here, that's indicator of the accuracy. So you need to carry those 2, 3, 4, 5, 6, 7 significant. When you divide this number, 7.8 by 4.235, you come out with that number. What is the least number of significant figure? 1, 2 here, 1, 2, 3, 4 here. So 2. So you only need to keep 2. Notice that the 4 was less than 5, so we just left the digit as is, 1.8. So look for the bottom, the smaller significant. That would dictates what the result is going to be. So now let's understand what counts as significant figure and what doesn't. Look at these numbers: 24.5, 345, 2.67. All of these have three significant figures. Here, you have zeros in between numbers. Those also count as significant figures. So you have 1, 2, 3, 4, 1, 2, 3, 4, and so on. When you have zeros before the number, those are called leading zeros. They don't count as significant figure. Only these two, 3 and 4, 6, 7, and in this case, 0 and 1, in this case, 2. So all of these have two significant. The trailing zeros are important because that's a placeholder. It tells you want to carry the operation to that kind of accuracy. 35.00, okay, 4, 12.100, you have 4 here. 234.0, you have 4 significant. Now, if you have just a whole number with no decimal, that's kind of ambiguous. It can be 4, it can be 2. It all depends how you write it. So that's why one of the reasons is good to write the power of 10 to indicate that how many significant digits are there. Because if you write this as 55.00, 10 to the 2, that tells you that you have to count these zeros, 1, 2, 3, 4. So that's 4. You have to carry the operation with 4 significant digits. Now, if I write that as 55 times 10 to the 2, that also gives me the same number. But it indicates that I only need to carry these with 2 significant. Okay, so you see the difference? All right, so we like to represent large numbers with the power of 10, as we mentioned earlier. Okay, so 5 million, rather than writing all these zeros, you just say 5 point, and you indicate that this has 3 significant. And small numbers, so there you go, 10 to the minus 7, 1 significant. Look at these numbers. Here represents 4 significant digits. Here represents 3. And here represents 2, 2, and 1. So, and you write these all in the power of 10. Now, rounding up, rounding down, as I mentioned earlier, depends on the digit that is after the ones that you have to round up or round down. Now, you have 2 numbers here, 74632 and 74391. Okay, so if you want to round this up, this one, say you only want to keep 2 significant digits, 7.46. So 6 is greater than 5. So you have to have 7.5. This one, 7.4, but the next digit is 3 below 5. So you ignore and just write down the 7.4. Some examples here. So you multiply these two. So how many significant digits here? 1, 2, 3, 4, 5. How many here? 1, 2. So you only have 2. So when you do this, you only keep 2. There you go. And you can write this in the form of 0.0063. You can write this as 63, 10 to the minus 1, 2, 3, 4. Or you can do this one, round 3 significant. So 1, 2, 3. So because it's 5, so this should be 7. Okay, there you go. And this one, 2 significant. You just ignore the 2, so you keep 2. You can write this as like that, the power of 10. Now we're going to see some simple problems that we have to kind of handle and solve. So the important thing is to read the problem and find out what is related to, what phenomena that we learn. And then find out what is known quantities and write those down with the unit. And then unknown quantity, what are we looking for? And then find out what formula needed. Okay, is it velocity? Is it acceleration? Is it energy? Is it power? You just write down those and see what variables are there. and use the known variables and find unknown. And then you carry the operation, keeping in mind the significant digits, and use the power of 10 as much as possible. Let's do an example here. Earth is orbiting around the sun in a circular motion. So here's the sun, and here's the Earth going around. Radius of 93 million miles. R is equal to 93. Well, I can write it in a form of zeros, which not very good. So I says 93, 10 to the 6 miles. So how many kilometer does Earth travel in one revolution around the sun? So one revolution around the sun, meaning that we want to have C, which is the circumference of this orbit, is equal to 2 pi r. So you can just simply write down 2 times 3.14 times r, 93, 10 to the 6 miles. So that gives you the circumference in miles. When you multiply that, you get what? 5.8. Now, let's see how many significant figures we have to keep. Look, 3.14 has 3 significant digits. 9.3 has 2, so we only need to keep 2. So 5.8, 10 to the 8 miles. It's asking us how many kilometers. So he wants to convert to kilometers. So we have to look it up. We know 1.609 kilometers is equal to 1 mile. Okay, so all we have to do, just multiply that. Miles and miles cancel out, and we are left with this number. How many significant digits? Let's say that this is 2, but this is 1, 2, 3, 4. So we have to use the least. So we use 2. So we have 9.3, 10 to the 8 kilometers. In studying science in general, you have to be careful because there's a lot of fictitious things that are called science. We call it pseudoscience. They're not science. They're just hodgepodge with no proven experiments. And people like to believe in some pseudoscience, astrology, reincarnation. But that's only a belief. You cannot scientifically prove or disprove any of these. So those are called pseudoscience. And you need to distinguish them from the science. Always ask questions. Are these claims are true? And is there any alternative explanation to them? Can you prove its wrongness? Remember, hypothesis. Is there a way to prove it wrong or right? And has it been tested? All of these questions you need to ask in order to separate, distinguish between pseudoscience, real, honest-to-goodness science. Okay, so this ends the chapter 1, and please review this, and I will assign a homework quiz for this, and it will be due Sunday. So see you next time. Thank you.